Yeah, in this video, we will be discussing the two MA2B2 square planar isomers. So A and B represent two unique monodentate ligands, and M is the central atom. Typically, that's a transition metal. So first, how do you figure out these structures? Well, uh, like a lot of these sorts of problems, what we've been doing is tracking pairs that are across or trans from one another and doing this in alphabetical order. So the most alphabetically advanced uh, combination of trans pairs is going to be AA, then followed by BB, right? Because we have two A's and two B's, and we're going to have two pairs of trans ligands because we have four pairs in total. Then we work our way down the line alphabetically. So after AA becomes AB for our first pair. That forces this one to also be AA. After AB, there's nothing else we can do, so we could do BA, but our rule is that we never have a reverse alphabetically listed pair. So BA is the same as AB, so that would just get us AB, AB again. And lastly, we have BB. Well, that would get us AA, which is what we had above, so that's redundant. So we have two answers here. We have the ones where A and A are trans from one another and B and B are trans from one another. And then our other answer is where A and B are trans from one another and A and B trans from one another. Now we could write this in some other fashion. For example, we could write this a slightly different orientation. As long as we have B and A trans from one another and B and A trans from one another, there will be some rotation. In this case, it'll be a 180-degree um, rotation that interconverts these two things. So these are one and the same isomer. These are called the trans and the cis isomer. So this is a very easy example to see that there's only two here. None of the square planar complexes, these generic complexes, are chiral because they contain a mirror plane in the plane of the molecule. There's other mirror planes in these examples too. But we use this systematic method of keeping track of trans pairs. This method helps us solve more complicated examples, going even beyond square planar geometries, for example, octahedral geometries.